Swayam Prabha. Digital India. Educated India.
So, good morning and welcome back to NPTEL lecture series on classics in total synthesis. So, yesterday we talked about total synthesis of epothelone by Nicholas group. In fact, we discussed two syntheses of Nicholas group. So, today we will discuss two more total syntheses of epothelone A, one by Schincker's group, the other by Danishefsky's group. The Schincker's group, what they wanted to do was, again they wanted to use the aldol reaction, the highly selective aldol reaction as the key reaction, and then also the ring closing metathesis as the key reaction to get the double bond followed by epoxidation. So, if you look at the retrosynthesis, on the right hand side the aldol, the cleavage of aldol followed by the ring closing metathesis, you can see the left hand side you have this homoallylic alcohol, right hand side the aldehyde. This is almost similar to what Professor Niccolo has done, and the southern hemisphere is this ethyl ketone. In the case of Niccolo's group, this used to be carboxylic acid. Here the 1,3-diol is protected as a ketone. Okay. Now, these three fragments were synthesized using the standard asymmetric route. Now, let us see one by one how his group synthesized all the three fragments. Okay. First, he carried out a Reformatsky reaction on this ester with 3-pentanone. So, the alpha bromo ester upon Reformatsky reaction with 3-pentanone, you get this beta hydroxy ester. Okay. This beta hydroxy ester, then upon treatment with acid, it underwent dehydration to give beta gamma unsaturated ester. Okay. This beta gamma unsaturated ester was reduced to get the corresponding alcohol, then it was oxidized under Swan condition to get the aldehyde. Now, this aldehyde is ready for asymmetric aldol reaction. For asymmetric aldol, he used a very interesting chiral auxiliary. So, what he used was this ester. This ester is obtained from mandelic acid. If you see, so this is mandelic acid. Okay. The mandelic acid ester, upon treatment with excess phenyl grignard, you will get the corresponding tertiary alcohol, and the secondary alcohol was acetylated. Now, this upon treatment with LDA, you generate anion here, and that enolate attacks this aldehyde, you introduce a chiral sender here now. Okay. So, once that is served, you have to remove the ester. So, reductive removal of the ester gives your chiral auxiliary as well as the 1,3-diol. Now, 1,3-diol, if you rotate it by 180 degree, okay, if you rotate this by 180 degree followed by protection of this 1,3-diol with acetone, you get this ketone. Okay. Then you need ethyl ketone here, you need ethyl ketone. So, that is easily done by cleavage of this double bond to have the fragment A. So, the fragment A was easily synthesized in few steps using Reformatsky reaction and asymmetric aldol reaction with a chiral auxiliary derived from mandelic acid. Then the fragment B was synthesized using Evans chiral auxiliary. First this was deprotonated and quenched with heptenoyl chloride. Okay. Then deprotonation followed by quenching with methyl iodide. You could introduce the chiral center here with a methyl group, then removal of the chiral auxiliary with LAH gave the primary alcohol, and oxidation with TPOP, that is tetra N propyl ammonium perruthenate with co-oxidant N methyl morpholine oxide gave the fragment B, which is aldehyde. Okay. So, now aldehyde is ready, and then that side ethyl ketone is ready. So, now the fragment C, so which is made from 1,3-propane diol. So, you take 1,3-propane diol and protect one of the alcohols as TBS ether and then oxidize the other primary alcohol to aldehyde. This upon Grignard reaction, this upon treatment with Grignard reagent derived from 2-bromopropene gives this allylic alcohol. As you know, when you have allylic alcohol, one can think about Sharpless asymmetric epoxidation. But when you have a racemic allylic alcohol, one can think about Sharpless kinetic resolution. So, Sharpless kinetic resolution, you could get exclusively this alcohol. Of course, the yield will be less than 50%. That alcohol was protected as TBS ether and followed by ozonolysis, you get the ketone. Now, the thiazole unit should be attached to this ketone. So, that was done using stabilized Wittig reaction. Now, this phosphonate ester derived from the corresponding bromide was treated with butyl lithium as well as quenched with this ketone to get this double bond. Okay. So, now you need to remove the TBS group selectively, oxidize and then convert into double bond for the ring-closing metathesis. Okay. So, selectively the primary TBS was removed, Desmartin periodine oxidation gave the aldehyde, that aldehyde upon Wittig reaction gave the double bond. Okay. So, then you do not need the protecting group here, because that alcohol is required for the esterification. So, removal of the TBS gave fragment C. So, you could make fragment A, fragment B, fragment C. Now, let us see how he combined all the 3 fragments and then completed the total synthesis of epothelone. So, first he started with the ketone, that is the ethyl ketone, generate anion and then quench with this aldehyde. Okay. So, 1.1 equivalent of LDA generates the enolate, quench with aldehyde. So, you get the aldol product, remove the astronide. So, you get now the triol. Okay. Take the triol and then treat with TBS triplet. Okay. Now, all the hydroxyl groups, one primary, 2 secondary hydroxyl groups were protected as tri-TBS ether. Okay. Then the primary one can be selectively removed by treating with camphor sulfonic acid. So, now the primary TBS is removed, you have the primary alcohol. As you know, the primary alcohol should be converted into carboxylic acid to make the ester. So, that was done with excess PDC in DMF. So, once you have the carboxylic acid, already the homoallylic alcohol was already prepared. So, couple this with DCC, you get the precursor for ring closing metathesis. So, then the ring closing metathesis with Krebs first generation catalyst gave a mixture of cis and trans alkene. Okay. He took the mixture and then went ahead, removed the TBS groups, okay, to get the precursor for epothelone A. Treatment of these 2 alkenes, cis and trans, gave a mixture of epothelone A and the other isomer, and the epothelone A is the major isomer. That is how he completed the total synthesis of epothelone A, and as you know, the key reactions involved in this synthesis are aldol reaction, esterification and ring closing metathesis. Overall, he took about 16 longest linear steps and yield was close to 3%. The fourth synthesis of epothelone, which we discussed today, was reported by Danishefsky's group. Okay. So, here I have written the molecule in a different way. So, do not get confused. Sometimes any complex molecule can be written in so many ways, but people write the structure according to their convenience and then according to their retrosynthetic analysis. Okay. Now, let us see how ES synthesized epothelone A and what are the key reactions ES used. Danishefsky's group used two key reactions, which is completely different than the three syntheses which we already discussed. He used a Suzuki coupling, okay, and macroaldolization. So, that is the last step. He used aldol reaction, that is a macroaldol reaction, as the last step to form the macrolactone. Let us see how he has done. The first retrosynthesis is obviously the epoxide formation. That means the double bond is the precursor for epothelone A. Then what he thought was he can use a Suzuki coupling. So, that means this side you have boron and this side you have iodine. Then you can carry out a Suzuki coupling. So, that means he divided that molecule into 3 or 4 fragments. So, now if you look at these two fragments, this double bond upon hydroboration will give the precursor for Suzuki coupling. Okay, that can undergo Suzuki coupling with this iodide, vinyl iodide. The other side, you can see these two can undergo Wittig reaction to get the double bond. Okay. And this molecule, this particular molecule, in principle can be obtained between this substituted Danishefsky's diene and this aldehyde using hetero-Diels-Alder reaction. So, overall, if you look at the synthesis of epothelone A reported by Danishefsky, hetero-Diels-Alder reaction, Suzuki coupling and aldol reaction. These are the key reactions he has used to complete the total synthesis of epothelone. Now, let us see how he made fragment A. The fragment A, this molecule was prepared from rose ester. We already discussed about rose ester when we talked about total synthesis of discodermalide by Schreiber's group. Okay. Now, he did a hetero-Diels-Alder reaction between his diene and this aldehyde. So, that upon hydrolysis gave this 6-membered enone. Okay. So, in this process what he has achieved is 2 new chiral centers. 2 new chiral centers were established using this intermolecular hetero-Diels-Alder reaction. Okay. Now, the third chiral center he could introduce by reduction of this enone with lithium aluminum hydride. Okay. Now, using this chiral center, he carried out a cyclopropionation. The hydroxyl group played as a handle to deliver the CH2 group from the same side. Okay. The alpha cyclopropionation was carried out using Jarrett's protocol. Now, the cyclopropanes can be opened. How? If you use N-iodosuccinamide, then this can break and that will lead to oxonium ion and CH2I. The 6-membered ring will become oxonium ion and at third position you will get CH2I. Okay. So, that is what you get, that oxonium ion, if you use methanol or any other alcohol, that alcohol will attack and neutralize the positive charge on the oxygen. So, now you need dimethyl group. So, that means the iodide should be removed. So, that was easily removed using tributyl tin hydride. So, you got the methyl group. Okay. Now, the OMe is a lactol protected lactol. Okay. So, before you do something you have to protect this hydroxyl group. So, that was protected as triphenyl silyl ether. Okay. That hydroxyl was protected as triphenyl silyl ether. Then the lactol should be opened. So, the the lactol methyl ether, first it has to be hydrolyzed, then it has to be protected. But these two can be done in one step if you use propane 1,3-diol in the presence of Lewis acid. So, what happened? You form a lactol, the lactol is protected. Okay. So, once you have that, the free hydroxyl group should be protected again, and this is protected as TBS ether by treating with TBS triplet. Then DDQ, selectively the primary benzyl ether can be cleaved using DDQ to get the primary alcohol, which upon oxidation under Swan condition gave the aldehyde. Now, Wittig reaction, because you need to homologate. So, for homologation he carried out enol ether Wittig reaction to get the corresponding enol ether, which upon hydrolysis gave the corresponding homologated product. This upon Wittig reaction, simple methyl Wittig, you get the double bond. Okay. Now, the diethane could be cleaved using BiAB, that derivative of BiAB, and since you use methanol as a solvent, the aldehyde which is formed is in situ protected as acetal. Okay. So, now the fragment A is ready. For fragment B, he started with the glycidol, okay, which is commercially available, and protect the primary alcohol as tetrahydropyrenyl ether. Okay. Then open the epoxide. Open the epoxide with lithiotrimethylsilyl propane. Okay. So, that opens, and then you can see this chiral center is formed. Okay. That is already you started with the chiral center, and next you protect the hydroxyl as mom ether and remove the tetrahydropyrenyl group using PPTS methanol. Okay. So, once you have that, Swan oxidation will oxidize the primary alcohol to aldehyde, and treatment with methyl magnesium bromide followed by oxidation with tetra N-propyl ammonium perruthenate gave the methyl ketone. Okay. Now, this Wittig reagent, upon treatment with butyl lithium, you can generate anion, and quench with that ketone, you get this double bond. Okay. Now, the TMS group can be removed, and iodine can be introduced in one step by treatment with N-iodosuccinamide and silver nitrate. Okay. And this upon reduction with you can call it as hydroboration and reduction. Okay. So, normally if you have triple bond and then do hydroboration oxidation, you will get enol, but if you treat with acetic acid, it will just reduce the triple bond, that is syn addition. So, you get the corresponding cis vinyl iodide. Then the mom group was cleaved using benzene thiol and BF3 ethyrate to get the corresponding alcohol. This was protected as acetate by treating with acetic anhydride and DBAP. So, now the fragment B is ready. Already we saw the synthesis of fragment A, and now let us see how B and A can be combined. As I said, this double bond should be converted into corresponding borane derivative, so that he could carry out Suzuki coupling reaction. So, he took this A and treated with 9 BBN. Okay. So, then the terminal position you have 9 BBN, then Suzuki coupling with this vinyl iodide. Now, you could see the cis double bond is made. Okay. So, for the last step, that is a formation of macrolactone. So, what is required? The protecting group of the aldehyde, that is now acetal, that should be hydrolyzed to the aldehyde, and the intramolecular aldol reaction of the acetate with the aldehyde will give the corresponding aldol. So, para-toluene sulfonic acid removed the acetal to aldehyde, then the key reaction, that intramolecular macro aldol reaction, was done with potassium hexamethyl disaccharide. After the aldol, now you have to remove the TBS and TPS group. Okay. But if you look at this carefully, this TPS can be selectively removed. Okay. So, with HF pyridine, in the presence of TBS, TPS, that is triphenyl silyl group, can be cleaved. Then protect the other hydroxyl as TBS ether. Okay. Then you oxidize this hydroxyl group. If you look at epothelone, this hydroxyl should be ketone. Okay. But if you look at the precursors, all three are hydroxyl groups, are protected hydroxyl group. So, now you need this as ketone. So, that is why selectively one has to remove the triphenyl silyl group in the presence of TBS and protect the aldol, other side aldol as TBS ether, then oxidize this secondary alcohol to ketone. Now, you have to epoxidize and then remove both TBS group. Okay. So, that was done first by treating with HF pyridine for little longer time. So, both hydroxyl groups were removed, then followed by treatment with dimethyl dioxirane, we could get epothelone in good yield. So, overall if you look at this synthesis, the key reactions are Suzuki coupling. Okay. First is Suzuki coupling, then the macroaldolization. So, that is not easy. Actually, macroaldolization is a risk taking reaction for doing such a complex total synthesis, but somehow he succeeded in the macroaldolization to complete the total synthesis of epothelone A. Overall, it took about 20 steps starting from R-glucidol, and yield was close to 2.6%. Okay. So, now we will move to two more natural products and then complete the syllabus tomorrow and day after tomorrow. Okay.